When you and Mrs. Milburn finished up the last video, you were drawing some pretty amazing angles, like negative 980 degrees, which meant starting from the initial ray and moving in a negative direction down from the initial ray, you went around the circle negative 360, and then another negative 360, and then there was still another negative 260 degrees left. Negative 90, negative 180, negative 260, ended up about here. So the terminal ray moves somewhere like this. But you already expected it to be there because before drawing the big loopy angle here, you had added on 360 degrees. And it was still negative, so you added on another 360 degrees. And that was still negative. So you added on another 360 degrees until you finally came out to a positive 100. So a positive 100 degrees starting from the initial ray and moving upwards from the initial ray in a positive direction, counterclockwise, would end up right about there. So even though these are two very different angles, they are coterminal because their terminal rays ended up in the same spot. And life is like that sometimes. There are people who move very quickly in a positive direction. There are some of us who wander around backwards for a while until we finally get there. We end up in the same place, but we take a different route. The amazing thing is that for every single location around the unit circle, there are an infinite number of coterminal angles. And like most mathematics, they're going to have a formula for that. Using exactly what you did over here. So every angle has an infinite number of equivalent angles. And how they write it, that angle's coterminal to angle theta you do just what you did over there. Going to take theta, whatever angle we have, plus n times 360, where n is an integer. Now n can be positive or it can be negative. We're just going to multiply a number of circles. Could have negative 3 times 360. You could have positive 10 times 360. Add it on to our original angle, and we'll end up in the same place. So this is an amazing thing. By moving away from triangle trigonometry to circular trigonometry, we can now have angles with thousands of degrees. We can have angles that are negative in degree. We can have angles that aren't even in degrees. And even degrees aren't as simple as they look. We have several units for measuring angles, all of which are based on one full circle. The most common by far is the degree, which we've been using. And circle equals 360 degrees, which seems simple enough. But even degrees are not that simple. Hundreds of years ago, mariners discovered that when you're projecting out across the ocean, the degree is too large of an increment. So each degree was split down into 60 minutes. And even that proved too large, so each minute was split further into, you guessed it, 60 seconds. So if we have an angle of, say, 32 degrees, 30 minutes, 0 seconds. And they use the same little marks that we use for feet and inches, for minutes and degrees. In decimal form, there were no seconds here, and 30 minutes is going to be half of a degree. So this would be the equivalent of 32.5 degrees. And this is what we usually use now in the calculators. But you may see what they call a hexadecimal key or a degree, minute, second key on your calculator. It usually just has these three little marks on it. Also, if you're studying geography, longitude and latitude may be expressed in degrees, minutes, seconds. A revolution has lots of meanings in the English language. It's even a flea and tick treatment, but revolution is pretty simple. The circle is going to equal 1 revolution. So if we have 10 RPMs, that means 10 trips around the circle in 1 minute. Very logical. Also, very logical to scientists anyway, is the next unit, which is the gradient. And this is abbreviated grads. Scientists thought it was very inconvenient for a right angle to have 90 degrees because they were working a lot with percentages. So for the gradient, a right angle equals 100 grads. Which means 1 full circle is going to equal 400 grads, which actually makes as much sense as 360. Now this hasn't caught on very much outside certain sciences, but you will see on your calculator often a degree, grad option. On the scientific Texas Instrument calculators we use here, when you go to mode, you have those 3 choices: DEG, RAD, GRAD. So the gradients are still in the running. More scientists are happier with a radian. And as you know, that 1 full circle equals 2 pi radians. And we usually leave it in terms of pi, but you know what pi is, it's just a number, approximately 3.14. So you could say that one circle is approximately 6.28 radians. One reason scientists like radians is because they are not some artificial number superimposed by a bunch of people in a civilization. They actually come from the circle itself. As you saw in the last video, one radian happens when the length of the subtended arc, as they call it, equals the radius of the circle. That will give us an angle of 1 radian. Just one. So I'm going to try to do this, but we'll see. So if I measure the radius here, it's about 1.5 centimeters. So I'm going to try to roll this around from the initial ray around to 1.5 centimeters to about, this is hard to do, about here. So this angle, where the arc length, which they call S, is the same as the radius, that angle here is 1 radian. Sometimes they use a little subscript and put a theta sub r in there to let you know we're talking about radians. And in this case, we would just say that the angle measure is 1. If it has no unit attached to it, it's assumed to be radians, which means if you're talking in degrees and you forget to put the degrees on it, it automatically turned into radians. And you notice 1 radian is way bigger than 1 degree. So if you're working in degrees, got to remember to put the degrees on it. We could keep measuring 1.5 centimeters, 1.5 centimeters around. It turns out there are only a little more than 6 radians in the entire circle, about 6 1/4 of these big chunky angles to get all the way around the circle. There will be 3 of them just shy of halfway across. Well, suppose we don't always have 1 perfect radian. Suppose we just have a circle and some random arc length. I'm sorry, I cannot draw circles pretty like Mrs. Milburn does. So if we don't have just 1 radian, we do have a handy dandy formula. It's pretty short. To find the measure of an angle in radians, I'm going to put a little subscript r there. We simply take the arc length, it's supposed to be a c there, and divide it by the radius. How many radii long is our arc? How many radiuses could we fit in the particular arc? This is also written S for the subtended arc divided by the radius. So if we had an angle something like this, maybe. Initial ray, terminal ray, then we'd have our arc length, our intercepted subtended arc would be here. and we would divide by the radius. So if the subtended arc is 20 meters and the radius is 10 meters, then to find our angle in radians, all we have to do is divide. So the angle in radians would be the arc divided by the radius. So it's going to be 20 meters divided by 10 meters, and the meters cancel out. The angle in radians is just 2. It has no units attached to it,